Okay, so here's our demo. At the end of class last time, we did, or in class last time, we did two programs, and we're going to demo them. The first one was figure 6.21. So here's, with this great little help system, we can copy to source. And so here was the C++ program. Now, what did we do for this C++ program? Over here, we had these global variables, right? Remember that? Num points, value, and j, and they were global, and then we had this print bar. And then we spent our time in class translating to here. And so now here, isn't this great? Copy to source, boom, there it is. All right, and so here is our program copied to source, and then we build it by clicking this little hammer icon, and there it's all built. And notice that we have these trace tags to trace our globals here, and then we have these trace tags to trace our locals, and then we actually allocate the local here, and we have our trace tag to label the K, the local K. All right, and so here's our listing if we want to see it. It's nice and have you guys used this format from listing? Yep. Is that slick or is that slick? Yeah. Okay, I'm glad you like. Yeah, I'm glad you like that. And so here's this input. Okay, so now let's start debugging. Boom. Now is this neat? Here you got j, value, and num points. We had that on the board last time, and they're global, so they're at the fixed location in memory. And here's the actual addresses at which they are stored. And as we single step through here, check this out, sports fans. We branch to main. We load accumulator. We decimal input into num points. So num points got the 12. Notice the 12 here got into num points here. And then we go to the next one. And now we load accumulator. And so now the accumulator has 1 in it. And then we store that to j. So there's the 1 goes to j. Is that neat? Mm-hmm. Okay. And then we branch if greater than. We decimal input value. And now, so we put that in D, and now we store accumulator at -2. And now when we do sub SP, notice right here we're about to execute sub SP. Are you with me? And what happens when we do sub SP? What happens?
Allocate.
Allocate. So boom, there's the runtime stack. So there's n on the runtime stack with the value 3. Is that neat? And then we do call, right? We just did call, and so that pushes the return address, and the return address is 49. Now, why is the return address 49? Because if you go here,
that's the memory cell.
That is this 49 right here, which is the address after the call. So the program counter has been incremented, and that's the 49 from there. Are you with me? And then, boom, so there's K. And now notice, like we mentioned yesterday, it's all in bold here. That is the what? All these three things are called a what?
The stack frame.
That's the stack frame. Also called, another name is what? Starts with an A? Yeah, you were the one who said it.
Activation record.
Activation record, okay.
That's good.
All right, and so now we go, now we're it's going to go 1, yeah, press return here, 2, 3. Okay, and then, I went kind of fast through that. But anyway, it deallocates, okay, and then it calls it again, this time with 4. So now we're going to print 4 asterisks as we go through that loop. So check this out. 1, 2, 3, 4. And now we go back up to the test, and we branch if greater than to N4. Oh, wait. Oh, no, it's not 4, it's 13. Oh, I don't want to have to do 13 of them. Maybe I will. Then, no, I get, well, anyway, you get the idea. Okay, so we just resume. That'll take, by the way, look, I know what let's do. You can do breakpoints here. You guys know what breakpoints are when you debug? Do you guys know what breakpoints are when you debug? You never heard of breakpoints? Oh, you should know this. Okay, check this out. What we can do is we can put a breakpoint. That's what these boxes are. So if you ever want to stop somewhere, so you can put let's say that you want to do a break inside the loop right after this character output. So you click this break, and now when you do resume, it will resume to that breakpoint. And boom, it resumes to that breakpoint. See, if you put two breakpoints here, let's put 2 breakpoints here. We'll put one here and one. We'll put one here and one here. So now, if you resume, check. See, and now this resumes. Now this goes all the way through and then resume, and it stops at that breakpoint. So when you press resume, it will go. It resumes until the next breakpoint. Do you see what I mean? Mm-hmm. So you can stop it wherever you want to in a loop if you want to inspect something. Is that cool? Mm-hmm. And then this is typical debugging stuff. And then if you don't have any breakpoints, if you resume, it'll just go to the end. Is that slick? Mm-hmm. I just think that's slick. All right, and now, so the next one is, so that one was 621. Now the next one we did was 623. And 623 is the same one that we had before, only now what did we have over here? What kind of variables? Local variables. And so we just worked through all the code for that in class last time. So here we'll copy it, we build it, so here it is. And now, if we start to debug, now check out what happens. So now we'll single step through. And now the main program does sub-SP. And why did the main program do sub-SP? Yeah, so boom, there's a local variables. Got it? Non-points value, ta-da. Yeah? Mm-hmm. Are we good? And then 12, blah, 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 blah. And now whenever we sub-SP, the stack is getting put on top of the stack that was allocated on the main. So boom, there's the N. Okay, notice that it's one at a time. And then the call puts what on the runtime stack? Return address. Boom, there's the return address. And then the sub-SP allocates local for the K, and so what is that? Boom. And there, it's nice and bolded there, so you can see which one is the stack frame. Is that slick?
Only been labeled as stack frames.
Well, I mean, each cell, yeah, well, whatever. Always want more. Users always want more. Okay, so there it goes. And then, so now the stack frame is being allocated and deallocated on top of the stack frame for the main program. So there it goes down, yeah? And so on. And then if you resume, there it goes. And so we had all of this little bar chart thing worked. Yeah? Are we good? Okay, so that concludes the demo. Okay, so we started with the demo, and now, coming due Monday is the second big milestone. And I will tell you that once you get this milestone done, you're home free. Usually in most code generators, the code generation is the hardest part, but we're not doing any optimization, and it's pretty mechanical to do the code generation. So this will be the hardest part of your project, at least time-wise, I think. Now, did you have a question about?
Yeah, I was looking at this yesterday, and I'm really having trouble switching out of the tokenizer and working with the parser.
Okay.
There's finite state machines, but there's inherent differences.
Yes. Okay. I think we'll go over the code for this. And you were asking about the buffer.
Yeah, we do need an in buffer.
Yeah, the in buffer works exactly the same way that the in buffer worked before. In fact, we'll get to that. In fact, okay. So let's start with now this code, of course, is not in the book because we are doing the project in Java, and the book is C++ oriented. So we're using, and the text uses C++ to implement the translator because that's the same language that we use as the example language for the memory models. And so it just seemed good to have it just be one HOL6 language for the book. But for us, we want to do this in Java. So this set of slides is different from the set. There's two sets of slides for chapter 7. There's the regular book version, and then there's this Java version. So anyway, all this material is on here. Oh, speaking of which, I have a warning. I have, in preparing these slides for this, I made some changes in the code. So you had better make sure that you refresh your, your browser and refresh the download stuff, because I renamed I did a little refactor. I used that refactor thing, and I did some renaming. So
How recent did you do that?
I did that a week ago, or maybe 1 to 2 weeks ago. So, but anyway, just make sure that you But if you got the old version, the only difference is I just renamed. That's the only difference. But if you want to update it, and I also included a new slide. So if you're going, the slides are available, also. And I don't know, I've seen some of you guys use the slides. So if you want the latest version of the slides, so the slides have been updated to match the revised code. I don't think I changed any of the logic of the code. I think it was just renaming. So, but anyway, a small point. Okay, so now your question was the difference between the the finite state machine for the tokenizer and the finite state machine for the parser. Now, so here is the finite state machine for the tokenizer. Notice that the tokenizer, as before, this tokenizer has a private variable, a private attribute named B, and its type is in buffer. And here at the bottom of the slide, we see the constructor for the tokenizer, and as usual, it gets the in buffer. It takes a reference to the in buffer that has been allocated somewhere else, and it sets B to in buffer so that whenever the tokenizer works, it has access to the buffer. So what the tokenizer gets from the buffer is a string of characters, right? Terminal characters. Now, I don't think we'll spend too much time actually looking at this tokenizer, because it basically works the exact same way that the tokenizer for the previous example worked. And I don't even think I have a finite state machine diagram for us to look at, but does this format of the code look familiar? I mean, it just goes in, there's some states, there's a start state, and if, util.is digit next char, so it checks if next char is a digit, and if it is, it sets da-da-da, and it converts the numbers to the strings to the numbers and so on. Okay, so there's that, and here it is, another section of that code, and then here's the identifier state, and here's the ls sign, so ls is lexical state, blah, blah, blah. But the main thing that we just want to look at is, what does this return? It returns a what?
An abstract.
An abstract token, right?
That's what we do.
Now within those tokens, there are, actually maybe we should look at what those tokens are.
The token classes.
Yeah, the token classes. Did we look at that before? Let's look at this.
Those are the states.
Yeah, those are the states.
Well, didn't we have like the identifier
We have T.
addressing
like T
mode dot
identifier.
blah? I mean the.
That's for our
T integer.
Yeah, we have to, it's confusing flipping back and forth between ours and this one.
This is new stuff though.
Wait a minute.
But the classes, the tokens and the abstract, those are what we are.
Oh, we did look at this. Here on figure 7.40, we did look at what an abstract, no, this was abstract code.
Mm-hmm. Yeah.
Did we also have one for the tokens? Oh yes, we did, here on figure 738. Okay, so let's review this for a minute. So the identifier token has a string, and then it says, and then it also has a method, and the string is private. That's an attribute, private attribute.
Constructor.
And it has a constructor to set it up. But then it also has a getString value, okay, that returns a string. All right, and the integer has a getInt value. So the tokens have the information in them. The identifiers have the information in them for a string, and the numbers have information for the numeric value. All right, and so this will be similar to what your tokens have, right? Your tokens are like what your tokens have. Your tokens have attributes and methods. Now, do your tokens have methods like this?
They have a
already.
description.
Yeah, they have some gets anyway.
So we have to
So it's like this.
Do we have to make new functions to match?
Well, you'll see.
Oh, awesome.
Yeah, okay. Okay, so those are the tokens, and now let's review this figure 7.40, and then this, now I think we've gone through this, right? This is the UML diagram for an abstract code class. And so you have a code, and what it has is generate code and generate listing. So each record, each line of code has a function that will generate a code, and it also has a function that will generate listing. And what they do is they return string. They are methods that return type string. Are you with me? And then remember we went over this: error, empty instruction, unary instruction, one arg instruction, and two arg instruction. And then now, what's the difference between this symbol? What does this symbol stand for in a UML diagram? ISA, which means, and what? Yeah, you're right. That's ISA.
That's abstraction.
No. Inheritance. ISA, and this is inheritance. And then this one is what? This one is HAZA. And this one is, what do we call this? Do you remember what we call this? Yes, class composition. Okay, so that's a nice review of UML. And so you see the way this works on this UML diagram is that because a one arg instruction has a what? Has an arg, that's why we have the has a relationship to the arg class. Mm-hmm. And then same way with two arg. It has two of them, but it has a, so, yeah? So you can tell by the attribute, what's in the attribute, how that works, what that looks like. All right, now comes the crucial thing. Now comes and then we went through this code for the abstract code. Now, this figure 7.43, this is modified from what's in the book. Okay, is a UML diagram of, sorry, not a UML diagram. It's a finite state machine for the parser. Now, I'm forgetting if we went through this figure before. Have we discussed about this? We probably haven't? Okay, so let's take a look at.
We did look at it at one point.
Okay.
We looked at it because we did.
Oh, because you had to design your finite state machine for the parser. Yeah, we did. So we did.
Talked about it.
So we did. Well, but we understand how this works now, right? What it does is the transitions are on the tokens. Are you with me?
Right.
The transitions are on the tokens. And so, and you can tell that, when we start at the start state, then if you have an identifier, if the identifier is stop or end, then you go to PS, state PS unary, and if it's add, sub, mul, div, neg, and abs, you go down to PS function, and so on. And those are transitions on tokens. Now, so here is now the code that allows us to do that. Okay, first of all, do you remember the map examples? Mm-hmm. The planets?
The planets.
Yeah. And remember so the way we do these lookups, when we get a string from an identifier, is we use maps. So here is the maps that we're going to use. We're going to have we're going to have three maps. This program has three maps. One is unary mnemon table, another is non-unary mnemon table, and another one is the mnemon string table. So do you understand what the mnemons are? Mnemonics, and those mnemonics are like set. In this language, they're like set and mul and okay, things like that. And so what is the first? So now what does the first one? The unary mnemon table what do you look up and what do you get? You look up a what?
String.
A string,
You get a mnemonic.
and you get a unary mnemon. So this is how you can tell if you have just scanned a unary mnemonic. If it's in that table, you have scanned it. If it's not, you haven't. Are you with me? And then there's another table for non-unary mnemonics. So how can you tell if you've scanned a non-unary mnemonic? You look it up. Remember, there was a method that it tells you whether or not it's in the table. Remember that? From that map demo? So you try to look it up. If it's in that table, you have it. If not, you don't. Okay? And if you have it, what will it give? And if it's in there, what will it return back to you? It will return back the mnemon, which is an enumerated. Are you with me? Okay? Because the enumerated, see, look. The enumerated, let's go back to this UML diagram of the code. Notice here in figure 7.40 that what do we store in our unary instruction? What do we store? A mnemon. We don't store the string. We store the mnemon. Are you with me? You are not allowed to store the string. It's not efficient in your code.
So in ours, we're going to have an abstract code.
Yes.
But we're not going to have a 2-arg instructor and a 1-arg instructor.
Well, no, you should use different terminology, because what you're going to have dot commands, and you're going to have,
So, is this abstract code, like this is kind of equivalent to the abstract token?
No, I think
No, the code is not the token.
Right,
Don't confuse the code and the token.
We used and generated a specific token each time we ran through our lexical analyzer.
Yes.
And this time we're going to be using these, taking...
I will show, yes. Now, we haven't seen the code for doing that, but in a minute we're going to see how to take the token from the tokenizer and make an abstract code out of a sequence of those.
Great.
Okay? But the main thing I want to emphasize is, because of the reason we're using these maps and everything, is because you don't want to store the string for the mnemonic. You need to store the enumerated.
Okay.
Okay, is everybody good on that? I keep having to cycle through this. Okay, so those are the maps. And now here, do you remember which one is the hash? Which one do we use the hash for? Which maps are the hash maps? The ones where the first one is called the key, right? So which ones do we use the hash map as opposed to the one that's not the hash map? Do you remember what the rule is? Remember, why is the mnemon table, why did we say mnemon table gets new hash map?
Well, a hash map goes from the string to the mnemonic, and then the non-map goes from the mnemonic to the string.
Exactly. That's exactly what it is. So up here, we see when we populate the non-unary mnemon table, we also say new hash map. But here, when we populate the enum map, we don't say new hash map. We just say new.
Okay.
All right. Enum map. That's because the first one is an enum. The key is an enum. So now, is everybody clear on that? Because there's no need to that's one thing about a mnemonic, an enumerated. If it's the key, then it's an easy lookup. It's efficient lookup.
Do we have to set up these classes?
You have to set up your maps like the maps that you're going to need. Yeah, you have to set up the maps like you're going to need. Okay?
But isn't an enum map a Java class that we utilize?
Yes.
Okay.
Yes. Just like hash map.
Hash map is also.
Yeah. And they are instances. They are subclasses of map. Yeah. Okay, is everybody good? And you see how these are populated, right? You just have the mnemonic first, and then the string, and then how you want it. And notice that this one we're doing lowercase for the output. Okay. But how are we doing the input? I guess we're doing lowercase all the way around, huh? even when the mnemonics are,
Just for this.
even when the mnemonics,
Switched it to upper.
We did upper, but
do you want, oh, yeah, either way is fine, that's
does it
fine.
really matter?
No, it doesn't matter. All right. And now, here is the enumerateds for the finite state machine for the parser.
For the parts.
Okay, so that's just an enum, right?
And every one of the states in the machine is enumerated here.
Yes.
Okay.
So does everybody see how this corresponds to the finite state machine for the parser? Okay? Now, here is what I have new, to explain this whole thing. And now what I want to do with this figure is not in the book. There's not even a version of this figure in the book, but there's going to be next edition. Okay? Now, let's take a look at the translator. What we have here is just one class diagram of the translator class. Now let's take a look so that we can visualize exactly what the translator has in it and where it fits in the assembler. So the name of the class is translator. What's the first attribute that it has?
In buffer.
In buffer. Okay? So B is the name of the in buffer, and in buffer is its class. And let's skip down and take a look at the first method in translator. That's the constructor. And what is that constructor take? It takes an in buffer.
Okay.
So do you remember who actually allocates the in buffer? It's that first action performed. Because see, because at the very beginning, because the main program has access to the user interface.
Mm-hmm.
And so it gets the string, the source program as a string, and it sets up the in buffer that way, and then that instantiates a translator.
Yeah.
Are you with me? It instantiates the translator. So basically what's going to happen then is the main program, or it's not actually the main one, but the action performed one, but you know what I mean. So it instantiates the buffer, it puts the source program in that buffer, and then it passes a reference to that buffer to translator. Now, and then translator, so therefore translator has a in buffer as an attribute, all right? Now, what else does translator have?
A parse line.
Well, no, I mean after the in buffer, it has a what? It has a tokenizer. All right, because tokenizer is a class, right? Are you with me? And tokenizer has, and what's the method of the tokenizer class?
Token.
No. What is it? What's the method that the token? Get token. Yeah, it has get token. So now does everybody see? Because translator has a tokenizer attribute, and the name of that attribute is T. Then it can execute T.getToken. Are you with me? Is everybody clear on that?
Okay.
Okay. And then the other attribute the translator has is lowercase a code, and its type is what? Capital A code. So that's one code object. That represents one line of code.
Just one line.
Just one line. Oh, I take that back. I did change some of the code.
Okay, I'm gonna have to redo mine now.
I mean, if you got it a few weeks ago, you might be working with some slightly different.
Is it only the translator?
Oh, no, I'll show you when we get to it.
Okay.
All right. Now, okay. So now let's think. Now let's see what the operations are in translator. Okay. First of all, we already mentioned that the first is the constructor. Now, the next thing that the translator has is a method called
Parse line.
parse line. this is one of the things I changed. I changed the name of it. Obviously, what does parseline do?
It goes through
It
our
parses
right?
a line. One line.
And says yes or no.
And check it out. It is of type Boolean.
Yes.
Now so that means that it does two things. First of all, it parses the line.
Make sure that it's a correct line of code.
Yeah. And actually, it's summarized down here what parseline does. It implements the parser finite state machine for one line of source code. It sets a code to the code object from the parse. Now, how can it set a code to that? Because a code is one of the attributes. So do you see that because it is a translator method, it has access to the attributes of the translator? Does everybody see that? Okay. And then the third thing it does is it returns true if it has processed the end statement.
If it gets to the final state.
No.
Okay.
No. Remember, one of the instructions is end.
Oh, so it'd be dot end.
For you, it will be dot end. That's the sentinel for the assembler.
So this will go through everything. The entire.
Well, okay. Translate. Now check this out.
Right.
So what will translate, so let's think about what translate will do. Translate will translate the whole thing, all the source code, but it will call what in a loop?
Parseline.
It will call parseline.
But how does parseline get to our dot end instruction or statement?
Parseline parses a line of code, and in the end, it will be able to detect if it has in fact parsed the end instruction.
Okay.
Are you with me? This is really important.
Because parseline's getting called all these times, it's going to be false until it reaches the very end of the statement where it becomes.
Well, until it parses the end statement,
Okay.
and then it will return true.
Okay.
And so what's going to happen then is see, look, there's two main methods of translator. One of them is called translate, which gets called from the main. And then the other one is parseline. So translate calls parseline. But the important thing is that both translate and parseline have access to what? All the attributes of that class. And what are the attributes of that class? They've got the buffer. They both have access to the buffer. They both have access to what?
The tokenizer.
Tokenizer.
And the code.
And they both have access to one code, one piece, one line of code.
And every time parseline is called, it changes that line.
Yes, and every time parseline is called, it changes that A code, and so translate has access to that A code that it changed.
Okay.
That's how it communicates. Yeah? And then the other thing that parseline does is it returns true if parseline has processed the end statement. Now, does everybody see who has access to what? How both, because there's two things here. There's translate method and the parseline method, and both of them are have no parameters. Are you with me? Is everybody clear? All right. So here goes the code, but we keep that in mind. So here comes the code. So check out translator. Here is the translator code. So public class translator, private end buffer, private tokenizer T, private A code, right? Corresponds to the UML diagram. And here's the one line constructor, right? Just sets the reference, okay, so that B refers to the buffer that's been allocated by the main program. Now, check this out. Now, keep in mind that the code that we're going through here, we're not doing parseline. We are doing so we're going to look at this, we're going to do this code walkthrough from top down. This is the code for translate. Are you with me? So let's see what translate does. Oh, sorry, just the opposite. Darn. Okay, we're going to go on this. We're going to go the way it is in the order that it's here. So now let's take a look at parseline. Now remember what parseline does. It assumes that we have a stream of tokens coming in, right? So what is it? So what do we have? We have some local variables. Boolean terminate gets false. With me? Abstract now here we have an arg, and this is a local first arg. And we have another arg, and that's a local second arg. And here we have a mnemon, which is a local mnemon. Now why do we need these locals? Because as we are getting those tokens, we are getting information from those tokens. Are you with me? And we're storing that information in these local variables, and then when we get to the end of the line, we know what kind of code we have. And so we use the information from those to construct our abstract code, our code object. Are we good? Okay, so what local variables do we have? Terminate, which is false, local first arg, local second arg, and mnemon, a local mnemon, okay? And by the way, I have a little note here. The compiler requires us to initialize some of these things, and some of these we don't need to initialize them, but that's neither here nor there. Okay, and furthermore, what else do we have here? An abstract token, which is called a token, right? And that's local. Because each time we go through the loop, what are we going to do? We're not going to get a character. What are we going to get? A token. So you see, that's the token we're going to get each time we go through a cycle on the finite state machine. Are you with me? So look. A code gets now which A code is this? This is that one that's the attribute of the class, right? So we initialize the A code to be new empty instruction. Yeah? So we started off to be a new empty instruction. And what do we set? And then we have another local variable called what? State. Yeah, and its type, its class is parse state. Right? And so what do? We just use the direct code technique for implementing a what? A finite state machine. Only this time, instead of getting a character, what do we get? We get a token. Are you with me? So look, here's how they're linked. What's the very first thing we do? Do, and then what? A token gets what? T dot get token. We just got a token. Now how did it get the token? Ooh, it went through all of it. It spun through and, yeah? Are you with me? And then switch state. And now here's the code. Okay, so here's what the first line is. Notice we say if a token instance of T identifier, right? Now, if that is true, we know that the static type of a token is an abstract token, but its dynamic type can be one of the specific ones. Are you with me? So it's impossible to use the a token to access the fields that are specific to the specific one. So what we need is a local, we need a local T identifier, which is a specific one, and then we typecast the a token to be the specific one. Are you with me? Because see, the T identifier is a specific a token, so that is a typecast. And then from now on, what we do is we use local T identifier instead of using a token, and the compiler will accept that because T identifier has the methods for an identifier that we need. So that is a typecast. Did everybody follow that? Are you with me on this? Okay. And then string, and then same way. Okay, so well, it's not the same thing, same concept. But on the next line, we have temp string is of type string, and that gets now we can say local T identifier dot get string value, And why can we do that? Because local T identifier has a method called getStringValue. The thing of it is that A token does not have that. See, we would like to say, I mean, it would be nice if we could say A token dot getStringValue, but A token doesn't have a getStringValue. The general one doesn't have that method. The specific one has that method. Do you see what I'm saying? Now, does that clear that up? Does the second line, you see the string, the temp string calls the getStringValue method of local T identifier. The thing of it is that A token doesn't have a getStringValue, if you look back on the UML diagram. So therefore we have to typecast it, we have to typecast that, the A token to a T identifier. And then we can use the methods for T identifier. Are you with me on that? All right. And now we just look up if maps.unary mnemon table dot contains key. So that contains key is the method, right? Okay. And then we give it temp string dot to lowercase. And if that's the case, then what have we discovered? That it's a what? That it's a unary mnemonic, right? Because we looked it up in the table, right? And if that's true, then what do we have? A local mnemon gets maps.unary mnemon table, get temp string to lowercase. And so we look, we get the mnemonic from it, right?
Yes.
And then now that we have the mnemonic, what do we know?
You know.
We know what kind of instruction that we have, and there's nothing left to do. So we do A code gets new unary instruction, we give it local mnemon, so that's the constructor. So now see, here's where we're using those locals to actually construct the abstract code. Are you with me? And then we say terminate gets what? Local mnemon equals mnemon m end, okay? And that's the same way we terminated our finite state machines always, right? And then state gets parsestate.ps unary, and we go to ps unary. Now, I think with this, and then if you just look through this, this is all this code. You know, here's the end of that state. Here's case ps unary, case ps function, case ps open. They all have the same format. They all use the exact same format of what we just did. The same technique, programming coding technique, of having to typecast from the general to the specific token, then using the methods of the specific token to get what you want, and putting those into, and then creating the correct A code, the abstract code. Okay, so here's ps unary, ps function, ps open, ps first operand, ps non-unary, ps comma, and now at the very end it's while what? State is not equal to parsestate.ps finish and not a code instance of error. And then what do we return? Terminate, because terminate, that's the Boolean that gets returned. And A code has been set. See, like here on this very last one, PS non-unary, else A code gets new error, illegal trailing character. So you know it sets it and returns that. Okay? So that's basically it for the parse line. And then the code for translate it's very straightforward. But I think you should be able to do it.
What part of the project is due on Monday? Is this whole thing?
This whole thing, except that, okay, let's take a look at translate. Except for it appends there's a data structure called an array list in Java, and what it lets you do is it lets you append elements onto the end of the list, and so we collect as we parse another line. We just stick it on the end. We stick it into this into this code table. All right, and here here with this code, there's two sections of the code. One of these sections says system.out.printf object code, so you just put nothing in there, and then you do the else part. You do this part, the bottom part, for int da-da-da-da.
Okay.
Wait, no, wait. Yeah, just, I'm trying to see where the listing was. I thought the listing was
It's the second one down.
else.
Oh, program listing, object code program listing is the system out, the first two system outs.
It's the, in the upper part. In the
Before-
Oh, in the upper part, sorry. Yeah, it's the wait. No, the object.
It's just,
Oh, it's the listing, right. So you can put, you can just do anything for the for statement for the object code, as all you have to do is the listing part.
so should we comment out the stuff from?
Sure. Or just not have it in there.
So not the object code.
This project that we're working on for Monday, it needs to have the tokenizer a part of it, along with all of the elements of the tokenizer.
Yes, it does.
And then it's going to take some assembly code and then just generate a listing of that.
Yes.
Okay.
And that code will be generated by this for statement, system.out.printf program listing, and then for int I get 0 code table.size I++, system.out.printf is, and then it will call generate listing. So you should have a generate listing, and that generate listing should generate the listing of the code.
Nice clean.
Yeah, as per the specification on the web page.
And do we need to have errors? So the next part is else, num errors equals 1.
Yeah. Well, do you want to have, okay, do you want to not have, well, but I don't see how you,
Errors kind of along.
errors, I mean, yeah, the errors, I mean, I don't see how you can avoid that. Because you're going to be detecting error messages. I mean, you're going to be detecting error codes.
We'll find, this will decide whether or not it's valid or not.
Yeah, and so you're going to have to generate, I don't see how you can avoid doing that.
Because isn't there some we have to check the address indexing also and see if that's an error?
Mm-hmm.
Okay.
Check if they're doing valid addressing.
So what you'll need is you'll need a map for the valid addressing, the letters for the valid addressing modes.
Is that
Do you see how
Would you
that?
like,
The
the key
mnemonic?
would be your instruction, and then you would be able to find addressing mode?
Yes.
for that one for the
Yeah, it would be the mnemonic.
Yeah.
It'll be a mnemon.
the mnemonic to the string? Is the string going to be comma space I? Is that what the string is?
However you want to.
Oh, for an address.
Yeah. To generate the code. Yeah. You can. Yes.
Okay.
Yeah.
And then
These are good. Yeah, these are good questions.
so in this code we have abstract arguments, but we don't have with abstract arguments we have like what are they? They're into
Well, no, but see, an argument, an operand specifier. What you have is an abstract operand specifier.
Okay, that's my question.
Are you with me? And what are the two kinds of operand specifiers that you can have? What can they be? What can an operand specifier be? It could either be a what? It could either be a hex constant or
Or an integer constant.
a decimal constant.
Decimal constant.
That's what that corresponds to. Are you with me?
I wasn't sure if you were going to tell us that.
We're not worrying about any character things at all.
Character things.
Character things.
So instead of AR, we're going to have
Our
a
translator,
spec
we're not
or something.
translating any instructions.
Oh, that have character constants.
Yes.
Right, that's not part of the spec.
Yeah.
Yeah.
Yeah. And one will be a decimal when we have constant. Yay, thank you for telling me that.
Oh, yeah, I'm glad to tell you, answer all your questions. Well, you have more? Do you have more questions? It looks like you have a list there. That was the main one?
I have a list of questions.
These are notes.
Oh, sorry.
It's just one question.
Okay.
And if we got 10 out of 10 on our finite state machine, that means we can just do this one?
No, I think you
There's
changed
new
it.
You know, if you want to change, if you want to modify the finite state machine that you did, that's fine.
I think we need to turn in a new finite state.
Yeah, that would be fine.
/ how do we,
Because now that you're seeing the implementation issues,
be
you might.
how do we implement, like, we have these footnotes for, like, only for this?
Well, that's when you do the lookup. That's
okay.
when we do the code and you look up the table and you see, oh, it is unary. It's not unary. See, that's how you do direct code technique.
Okay.
A that an okay name? AOP spec?
Say it again, abstract operand specifier, yeah.
AOP spec?
OPRND. Actually,
I was gonna say AOP SP.
well, in the text, operand is OPRND, that's kind of what we use.
Spec? Operand.
Yes, but yeah.
Okay, operand spec is kind of cool.
Kinda.
Well, whatever, yeah.
Operand
So, shall I grade you on the coolness of your?
Sure, grade us the use refactor.
Okay, is that it? Any more questions? All right, well, it's way past time to go, so.
Will we be graded down? Bad labels.
Okay, so see you on Monday.